All right, inductive reasoning is what we're looking at today. And we start geometry with not chapter 1, but chapter 2, because we want to talk about the logic and the reasoning portion of geometry. One of the things that really does tend to stick in people's mind when they think about geometry is the idea of proving things. If you talk to your parents about their geometry class when they were in high school, they'll probably talk about doing proofs and all this sort of stuff and doing all this logic and writing conjectures and that whole bit. It's a little different now. We don't do as much of it, but we start with the idea of how we think and how we come to conclusions about different things, the way we can reason through information. So it's really not that mathematical in a lot of senses. It's more just logic and thinking and that sort of thing that we're going to talk about to begin with. So what we talk about here is inductive reasoning. We start with that today. And inductive reasoning is something that you do naturally. You do all the time. It's not a big deal, okay? Please, eyes up here, books and other stuff away, other classes. Want to keep you involved in what's going on in geometry when you're in geometry. Thanks. So look at this pattern here. I've got a pattern of stars. I have this star, then another star. What do you think should come next? Describe what you would expect to see next. What do you think?
Well, there should be 7 because it started out with 4 points and 5.
Good. 4-point star, 5-point star, 6-point star. Pretty reasonable to assume that the next one will be a 7-point star, right? And by the way, if you had to draw that, don't worry, I don't take off for bad artwork. One thing you will learn very quickly during the semester is I am not a good artist. I don't draw nicely. I can barely write sometimes. But we can still get the idea across. How about here? I've got a pattern of numbers. -7, -21, -63, -189. Describe the pattern to me. Multiplied by 3 every time. So if I wanted to describe my pattern in words, I would say multiply by 3. If I wanted to find the next number, I'd actually take -189 times 3, which would be, what is that, 27. 3 times 9 is 27. 3 times 8 is 24, plus 2 is 26. So 567 would be next. Okay? So we can both find the next number in the pattern and we can describe the pattern. But what we're doing is what's called inductive reasoning. We're finding a pattern in what's going on. And honestly, there's nothing wrong with inductive reasoning. We do it all the time. It's something we do instinctively. In fact, a lot of the scientific method that you learn in science class is based on the idea of observation and then prediction, isn't it? You observe what happens, you observe what happens, you observe what happens. You see it happen often enough, you start making predictions based on your previous observations. That's inductive reasoning. And it's fine. There's nothing wrong with the idea of inductive reasoning. When you make a guess as to what comes next, that is a conjecture. You'll be asked many times, you'll see that word in problems. They'll say, make a conjecture about. What does that mean? A conjecture is essentially an unproven statement based on observation. In simpler terms, it's an educated guess. You're just making a guess. What's going to happen next? And so oftentimes you'll be asked, make a conjecture based on what you see. There's something you do all the time in science class. You walk down the road, you see 3 robins and another bird flies by. What do you think? You probably, in your mind, you're making a little conjecture. Oh, the next bird's probably going to be a robin too. So let's take a look at some mathematical conjectures here. 5, 6, and 7 are what are called consecutive integers. Let's look at several examples of the sum of 3 consecutive integers, and let's see if we can make a conjecture based on our observation, a mathematical conjecture. So I have the 5 plus 6 plus 7 equals 18. Okay, easy enough. 10 plus 11 plus 12 is 33. Yep, I can figure that one out. 25 plus 26 plus 27 is 78. All right. 99 plus 100 plus 101 equals 300. Does anybody notice a pattern relating the numbers being added up and the sum? What do you notice?
The numbers are all like 5 and then 1, 4, 6.
Right. But we're given that they are consecutive integers. So that's something we're given. I want to see if we can find a relationship between the sum.
The middle number is 3 times the amount.
Okay, the sum is always 3 times the middle number, it looks like, doesn't it? That would be the kind of conjecture that we're looking for. It relates to a couple of different things. You are correct in saying that they are consecutive integers. That is correct. But the kind of conjecture that we're looking for here might be something more like that. So my conjecture might be the sum is always 3 times the second number, or the middle number. That's a conjecture. And if I try different sets of numbers, it seems like it usually works. But again, all this is an educated guess. We haven't proven anything is true. We're just making a guess as to what might happen next, or what the relationship between these things is. While conjectures cannot be proven true necessarily, they can be proven false. And we can prove a conjecture false by providing what's called a counterexample. The counterexample is a specific case for which the conjecture does not hold. That's what a counterexample is. So again, if you're looking for a definition for a flashcard, that might be something you might want to put on there, a specific case for which conjecture does not hold. So let's say I make a conjecture. The square of any number is greater than the original number. That's my conjecture. Well, I'm going to tell you right now that that statement is false. Can somebody give me an example, a counterexample, to show that that conjecture is false? Yeah. 1 squared. 1 squared, okay? 1 squared is not greater than 1, is it? 1 squared equals 1. So, fine. 1 would be a counterexample for that original conjecture. So, being a good math student, then we say, okay, we'll modify our conjecture. Let's modify it. Greater than or equal to. Ah, much better. Were we good now? Is that conjecture? Can we find a counterexample for that conjecture? Yeah.
0 squared.
Okay. 0 squared is greater than or equal to 0. 0 greater than or equal to... No, we're still okay. It's a good guess, though. 1 and 0 are great guesses, yeah. 2 squared is greater than or equal to 2. No, that's not a counterexample. It's still okay. In numbers, when we're looking for a counterexample, we did a good job identifying the first 3 that we normally try. We tried 0, 1, and 2 to see if they all work. So it's excellent thought process to try those nice simple numbers. What other numbers might we want to try? Let's not just stick to our counting numbers. Let's think about other numbers. There are a lot more numbers than just whole numbers. What do we get? Yeah. What about if the number is negative? Good idea. Let's try negative 1. Negative 1 squared is greater than or equal to negative 1. Well, but negative 1 squared is 1. Okay, so it is. My conjecture still is good. Haven't found that counterexample yet. What do you got? 0.5. Oh, 0.5, a fraction. What's 0.5 squared? Well, 0.5 squared is 0.25. Ooh, there we go. 1/2, 0.5. We found a counterexample. Did it take us a few tries? Yep. It took a few tries. But one thing hopefully you're going to get from this example very quickly is when you're looking for counterexamples for number problems, you guys picked all the right numbers. You did a really good job figuring them out. 0, 1, 2, -1. They're all good things to look for counterexamples. Usually they exist there, and if not there, we move to 1/2, a fraction. Usually if it holds true for all of those, then it's going to be harder to find a counterexample. Usually one of these things that we tried, 0, 1, 2, -1, and 1/2, my counterexample will usually be in that group of numbers. But again, it forces us to think outside just our simplest numbers of 1, 2, 3, 4, 5, etc. We've got to start expanding our idea. How about this? Jane is standing on the corner watching cars, doing a survey about the type of cars that people drive. Those are the cars that Jane sees. What conjecture might Jane be tempted to make based on her observation? Yeah.
The less expensive cars are going to be more common on the street.
Okay. They all look like pretty inexpensive cars. What else do you notice about the cars? Yeah. They're all red. Okay, so she might conclude that red cars are on the street. People drive red cars in the street. What else? Anything else that people notice? Well, they're all cars. None of them are trucks, right? That might be a conjecture. Every vehicle on the street is a car, not a truck. But let's say we went with the most obvious, I think, here is red, because color is a theme here. All the cars are red, so let's say she makes a conjecture that all the cars in the street are red. What might be a counterexample to that? Yeah, a yellow car. I just happen to have a yellow one up there, but blue would have worked too. Or green, or pink, or whatever color you want to make it, silver, black, a different color. So again, a counterexample accepts the basic premise of the conjecture, there are cars going down the street, but contradicts the conjecture's conclusion that all the cars are red. Or here, with the numbers, a counterexample, we had x squared and x, but it contradicted the conclusion that x squared was greater than, or in this case, equal to x. That's what a counterexample does. If my conjecture that every fish in Lake Koshkonong is a bluegill, let's say make a conjecture like that, what would be a counterexample? And let me give you a couple choices. Would a good counterexample be a fish caught in Lake Waubesa, or a fish caught in Lake Koshkonong that's carp? Option 2, because it accepts the idea that the fish is caught in Lake Koshkonong, but contradicts the conclusion that it's a bluegill. We don't contradict the premise of it being caught in Lake Koshkonong. Only in Wisconsin can we have like things like Koshkonong and Waubesa and stuff like that. We don't even blink at those words because we're so used to these Indian names for everything. It's kind of cool. Other states, they look at these words, Koshkonong, and then, okay. So you kind of get the idea of counterexamples. We can also use inductive reasoning to help us find out or figure out linear equations or relationships between numbers. Now this takes us back to Algebra 1. And you're going to find this all year long. This is going to be a really common theme. We are going to take a geometric concept here like reasoning, counterexample, and hypothesis and stuff like that, and we're going to learn something about that, and what are we going to do? We're going to go right back to algebra. So we're going to take that principle from geometry and apply it to algebra and see how it works in algebra. Linear equations can be found using inductive reasoning. And here we have a linear pattern. Now, I've got a chart here of x and y values. And some of you already probably got the equation already all figured out in your head, but let's talk through the process because this is something that's been a little while for some of you. What do we notice about the x values each time? Let's look at the pattern in the x values. What are we doing each time?
They're going up by 1.
Up by 1, okay? Someone else, how about the y values? These are going up by 2. And remember in algebra when we talked about rate of change, it was always change in y over change in x. What did we call that? What's the word we use for change in y over change in x? The rate of change in algebra. Describes how steep the line is. What? Slope. That's the slope of the line. We all remember the equation form y equals mx plus b, right? Slope-intercept form of an equation? Ringing any bells with people? How many are going, they never taught us that in Algebra 1? Okay, that's a lie, they did. You just probably don't remember it, it's been a while. We did. Okay, m represents the slope. So the slope here is 2 over 1, or just 2x, plus b. What does b represent in that equation? Who remembers that?
The amount of x values are going up?
No. The y-intercept, yes. B represents the y-intercept, or the value of y when x is 0. So I kind of have to, let's work our pattern backwards. So if this is 0, what's this going to be here?
2.
What are we doing each time? We're going to subtract 2 each time, right? We're subtracted 1 this time, so here I have to do minus 2, so 3 minus 2 is 1. And I've got an equation, a linear equation based on inductive reasoning. Now, that did require us to work backwards and remember some stuff from algebra, but I want you to see that this stuff is related. Geometry and algebra are always really closely related. And we use algebra all the time in geometry. And that's really not the focus of our lesson, but I want to tie things in. You will see a couple problems like that in the homework. Probably not so much in the test. That would be more of an extension type problem almost on the test. But we like to tie in the ideas of algebra into geometry all the time to keep that algebra stuff fresh in your mind, because a lot of you are going on to Algebra 2 next year. You need to keep algebra in your mind. Keep that happy. So we've got an equation, and again, we use inductive reasoning to do that. The weakness of inductive reasoning is this. Inductive reasoning is great, and we use it all the time, and it does a lot of really great things for us. But the problem is, when we reason inductively, we might come to a false conclusion. We saw that with the cars on the street. Jane saw 5 red cars in a row. That was great. But if she came to the conclusion that all the cars in that road are going to be red cars, that wouldn't be right at all, would it? She came to a false conclusion. So inductive reasoning is a great way to kind of work things out, but it's not foolproof. Because sometimes our conclusions are wrong. So there's got to be a better way, and that's kind of where we're heading tomorrow. So where we can actually prove that a statement is true. Not just reason inductively, but tomorrow we'll talk about reasoning deductively. When we do deductive reasoning, we can actually prove that something is true, instead of just being able to prove it's false with a counterexample in inductive reasoning. So what are we doing today in the homework? What sort of assignment do we have today? Well, as you could probably guess, we're doing reasoning. You're guessing the next number in the pattern, or the next picture in the pattern, or something like that. You're writing a rule based on what you're observing. What would the rule be? Are we multiplying by 3 or dividing by -2? Something like that. For 23 through 28, do not graph them. These are pretty quick little problems. They do not require pages and pages of work. They don't require you to solve long and difficult equations. They tend to be fairly straightforward. But just because I want you to have just a little bit more practice, I also have a very brief worksheet which should be fairly easy. It's just pictures. Find the next picture in the pattern. So the worksheet is included as part of the assignment. And you'll notice there's some vocabulary there too that we'll be going over in class tomorrow, but at least try to get those cards started if you can't get them finished. It always helps to pre-read the next section. It's a great study habit to get into, pre-reading, because then you have an idea what's coming up, and when you hear me talk about it, you've kind of seen it before, and it might click a little bit better. And if you don't understand something, you know what questions to ask right away. So when I say do this vocabulary and read that section, I really do mean look through it. At least find those highlighted words. Copy down those words. If you can get the definitions copied down, great. If you can't quite get the exact definition or don't exactly get it based on that, we'll go over it in class and we'll get it then. But at least you've taken the time to pre-read and kind of prepare your mind for that. All right? Any questions? Just a reminder that one of the expectations in here, or part of our accountability, is that we're going to work right up to the bell, which means a little bit after 11 o'clock. You've got like 18 minutes worth of work time in here. You'll probably be able to get through most of the assignment. It doesn't mean you have to sit by yourself in complete silence and do the assignment without making any noise. That's not what we're talking about. If you want to go to a neighbor and work with them on the assignment and go over stuff and talk about it as you're doing it, that's excellent technique. Some people learn best that way. That's fine. But if you're going to be working with somebody, you need to be working with that person, not talking about what your plans are for the weekend or stuff like that. Got it? And we're going to stay on task until about a minute left, and we are not going to get up and line up by the door and pack up for 5 minutes to go. We're going to wait till about a minute left before we pack up. In fact, I'll kind of give you a little clue when it's time to pack up, okay? Fair enough? Okay, sounds great. Have at it. If you have questions, by all means, call me over, come see me, whatever you want.